Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob Pease Show. Here's your host, Bob Pease.
Good morning and good afternoon and all those other good things. Welcome to the Bob Pease Show from the National Semiconductor Television Network. We're going to introduce our colleagues, Paul Grohe, Senior Product Applications Engineer. Hi, Paul. And the other Paul is Paul Rako, for which we also have a foil up here somewhere, Senior Apps Engineer and a Amplifiers Group.
Yep.
Hi, Paul.
How you doing, Bob?
We're trying to avoid confusing you with all the Pauls.
Okay.
We are also going to present something for our sponsor, Vishay Siliconics. And this show is sponsored by Vishay Siliconics, the leader in semiconductor solutions for low voltage, power management, and power conversion. Vishay Siliconics brings you the latest innovations in power MOSFET silicon and package technologies to help make your designs smaller, lighter, more power efficient, and easier to manufacture. Now, to see what these second-to-none technology strengths can do for you, visit Vishay Siliconics on the web. And as usual, we're going to be talking about all sorts of linear topics and linear stuff.
Yay!
We're going to be talking in the future about topics such as analog computing, vacuum tube op amps, precision milliohm bridge, 3-level graders. I forget all the stuff we're going to be talking about. And we're also going to mention some new products, such as the new LMV 771. And Paul, you can talk about that better than I can, I believe.
Yes, this is a nice little part. This is actually a low offset CMOS input, rail-to-rail output op amp. It's also a low noise part. So this is a good replacement for JFET type applications.
Oh, you don't have to have a JFET, right?
No.
And just to get the noise.
Yeah, and the nice thing is here it's 1 millivolt offset, and we guarantee that over temperature, which is the full industrial temp range, minus 40 to 125 C.
Wow. What's the supply current?
Oh, just 550 microamps.
And we get that kind of noise?
And you get, 9 nanovolts per root hertz.
That's awesome.
And it's in an SC70 package, so you can put it right up there with the signal source.
And it is CMOS.
And it's a CMOS input, so it's just like an old JFET.
In a tiny little package for good measure.
Yep.
Okay, I'm impressed. I gotta try some of these. And our major topic today will be what's all this wattmeter stuff.
Yeah.
We talked about this about a year ago in Electronic Design Magazine. But before we actually get into that topic, first, you're encouraged to ask me questions. You're permitted to ask me questions. We'll reply by email. We'll put some of the good answers on the webcast that we do next. So be sure to push the right button and send me a question. Now, this was a wattmeter that, it's hard to read this, but that's okay. This was, what's all this wattmeter stuff, from May 13th of 2002. And the text is available on the web. Oh, let me mention how you get there. You go to my main website, which is www.national.com/rap, and you click on ED columns and you search for wattmeter, and up comes all this good junk.
RAP like R-A-P,
RAP, yep.
All right. What's the middle A stand for?
Allen.
Allen? I like
Now, the simplified schematic, the simple schematic of the wattmeter is, if you have voltage, you have current. If you have current, it can be modulated because if you have a load current, forward or reverse, it can deflect the meter by making this act like a little modulator. You connect your load. If there's no load current flowing, there's no voltage here, then there's no deflection in the meter. Or if there's no voltage here, there's no current flowing, there's nothing going in the meter.
But as a differential pair, isn't the current down there always the same?
No, because this is part of your AC line current. So this goes to minus 110 volts, minus 160. When it goes to plus 110, plus 160, nothing happens. There's a clamp in here.
Oh, and it cuts it out.
So this is...
Works on the half cycle.
It works on a half cycle. The principle of operation says that the meter deflection is proportional to the base voltage, which depends on the IR drop in the milliohm shunt, and it's proportional to the negative V peak. It's proportional to the power. It is a true RMS reading meter. It works half the time, but it works perfectly half the time.
So it's as though this point is the bias point for here, and then as this goes up or down, then it increases the current here, and this is
No, it doesn't increase the current. It changes how much of the current splits into one side of the meter or the other.
Oh, okay, so it
This
is
can read
balanced.
negative watts. If you pump power back into here from a generator, you can make it read negative watts perfectly. Now, it only works, as we said, on 1/2 cycle. And we're going to discuss today some of the opportunities for improvement, such as improving the bandwidth, making it work for low voltage operation, better linearity, and better tempco. And the first topic we'll talk about is the tempco.
We have to pull them down a little, see how it's up off the top edge. Yeah. There you go.
We can do, here.
Excellent.
We did
Don't
it.
try this at home
Now,
with our trained professionals.
The original shunt, we'll show you in a short while, is a bird cage. We have a whole bunch of wires parallel in sort of a cylindrical pattern. You force in your 10 amperes, 20 amperes, 200 amperes, and you get a certain IR drop made out of copper. And I said, that's a really neat geometrical approach. I bet that has low inductance. You know how low it is? It's 280 nanohenries. That sounds wonderful. But 280 nanohenries actually says your 3 dB down at 600 lousy hertz, which means you can't use this circuit for a wattmeter as originally designed. We got to tweak it up. Now, first of all, I estimated it was 280 nanohenries, giving you a lousy 600 hertz. Then I measured it, and it was about 46 nanohenries, which gave about 4 kilohertz for 3 dB, which means you've got 6 degrees phase shift at 400 hertz, which means it's a lousy meter for audio.
Or airplanes.
For yeah.
400 hertz.
Yeah.
Now, why can't the bandwidth just be 60 hertz? Because it's 60 hertz electricity.
But if you're doing 60 hertz wattmeters, you may have transients that draw current during a peak, and you don't want it to draw at the wrong time. So this inductance would give faulty readings, even at 60 hertz.
So it doesn't have to be a resistive load. It'll work on
This is
anything.
a true RMS meter.
Oh, this is
The
cool.
meter is capable of working to almost a megahertz, but the inductance is not. So I said, boy, this stupid bird cage of wire, which we'll see in a little while over there, is not such a bright idea. What if we take a piece of insulated twisted pair, send out one wire not insulated and one wire insulated, and you wrap it around it to make twisted pair, and you put it across a 1 megohm resistor, which of course is a joke. And then you've got a low impedance piece of copper.
The mega ohm is just something to solder to?
Just something to solder to.
Okay.
And then you repeat this 12 times until it begins to look like an array of 12 twisted pairs out and back. Now, why twisted pair? For low inductance. And why is one of the wires not insulated? To get the heat out of there. We want to get the heat out of there. Now, I actually built this thing. The inductance is down about another factor of 7 improved. Now the 3 dB bandwidth is about 30 kilohertz,
wow,
which is not good for audio, but it's not terrible. That's for 1 milliohm. If we do this for 10 milliohms, we could have 5 nanohenries, 10 milliohms, 300 kilohertz bandwidth, and 6 degrees phase shift at 30 kilohertz. That would be pretty good for audio. And 10 milliohms will be good enough anyhow. And this is what it looks like. We got red wires and purple wires. Red is force, purple is sense, yellow is for cheating, because I was trying to bugger down the values. And these are the twisted pairs. And there's 12 of them, and 10 of them in parallel, and I could add some more if I need to.
Like a Medusa Hydra kind of look.
And this
to it
gives
there.
about 5 nanohenries.
That's great.
Next, let's talk about temperature compensation. This original circuit, as designed by Carl Nelson, was written up in AN 222 about 22 years ago. The original design has about 1 milliohm of copper wire, which is plus 3,700 part per million per degree C. So the gain will go up as this heats. That is one reason why we make these things so huge, so they won't self-heat. You make a 20-watt resistor running at 0.2 watts, it's not going to get hot. So this has a positive tempco. The transconductance of the transistor pair is at minus 3,300 part per million per degree C. The resistor tempco is negligible. So what you have left over is maybe 400 part per million per degree C. Well, it's not terrible, but it's not wonderful. To make it a little better, you could put in 1.1 milliohm of copper and 10 milliohms of low tempco resistor. And that's about 3,300 now. And that cancels the 3,300 pretty well. That would not be too bad. Here's an improved method, and I haven't built this yet, but I might. The transistor still runs at a mediocre, lousy 3,300 part per million per degree C negative. This runs at 50 part per million per degree C, because I got the data sheet on the Vishay WSL3637. We're going to parallel several resistors. And then we're going to put in a 10K negative tempo thermistor down in here, which will make this current about plus 3,300 part per million per degree C, which should approximately cancel out, and it might work very well.
Is the Temco, the 394, is the Boltzmann's constant good guy stuff on?
Yeah, that's the GM versus temperature. It's inherent.
Temperature, that's inherent in semiconductor physics.
So I haven't got a data sheet on the 10K thermistor. I'll go out and buy a couple of 10K thermistors someday. Here are some good Vishay Dale power strip resistors. Ooh. It's rated for 3 watts at 50 part per million per degree C.
They got Kelvin connections there, huh?
Yes, it's 4-terminal connection.
Ultra cool.
Now this is really big. It's like 0.36 inches square. Wow. So it's not as big as it looks, but that's okay.
And you still multiply them to, same thing, eliminate the self-heating?
Yeah. I'm going to use 3 or 4 of these in parallel. Depends on what I can get for samples. This is 3 watts. To get a lot of wattage rating, I can parallel some of these force and sense.
I've got a friend at Vishay. He may be able to get you some.
You notice that? Yeah. Good. Further possible improvements. Can we get better linearity? Now, in here, let's do the low voltage operation first. In the basic design, if this is minus 80 volts, you can ignore the VBE. But if this is minus 8 volts, no, you can't ignore the VBE. So it's easy to add an op amp where if you have minus V supply, this would be minus V supply, minus 1 VBE, this would tend to subtract out from this one, and this would work down at low voltages such as 2 volts or 30 volts, anywhere there. Now, I mentioned the linearity is not very fancy. When you get as big as about 15 millivolts of IR drop in the shunt, you're losing about 6% gain error. It's not a disaster, but it really is a definite weakness of this circuit. And furthermore, when you go past 15 millivolts, it gets worse and worse and worse very rapidly.
This would be the dynamic range of the meter, how as you push it to higher powers, then you're going to get a little inaccuracy. You
get a lot of inaccuracy. For 1 amp, it's very linear. For 2, 4, 6, 8, 10, 12, 20, it's losing several percent of error. You can compensate it out, but it's not a great solution. So here's a conceptual one. I haven't really done this, but on paper it might work. As this voltage goes down and down, you draw more current, 5 amps, 10 amps, 15 amps. This goes more negative. This is supposed to go more negative. This is supposed to go more negative. This is inverting. I got it drawn wrong. The concept is that eventually this will go more negative, and no matter how far this goes negative, this will go even more negative, making it effectively a linear circuit.
Did you spice this, Bob?
I did not spice that.
Oh, darn. We missed the spice, huh? Oh, well.
So we will mention that you can have several ranges. You can have 1 milliohm plus 9 plus 90 equals 100 milliohms. You can have several ranges. We got several ranges over here. We did not use a rotary switch. We used gang switches, namely click, 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 click.
This is published on your website, right?
That is published on the website. If you go to www.national.com/wrap and you click on ED columns and you ask for a wattmeter, all of this good stuff comes up.
WRAP, R-A-P, not W-R-A-P. Yeah.
Now we're going to have some new National Semiconductor linear seminars. Let's put that in this envelope.
Okay.
Yeah.
We're getting
coming soon to a city near you. Namely, we're coming to all the 30 cities we went to last time in U.S. and Canada, plus one more, which is Austin, Texas.
Excellent.
And we're going to be talking about the art of analog and how to build amazing things like 1 ampere current sources. And if you had an eye chart, you could read, oh my God, well, you can find this from the web, all these 31 cities. And I'm not going to recite them all.
We're doing Europe after that.
Well,
next year.
Shut up!
That's a secret?
No. To register to attend this, go to www.national.com. If you hit /RAP, you'd get there anyhow. And also, we are coming to 22 cities in Europe.
I didn't know we were going to Europe.
In November, approximately. Late October and November. And sign up. Next, Paul Grohe is going to work over there to fix up some of the things I screwed down on my experiment. He's going to screw them up. And we're going to have a word from our sponsor, which is our guest, Derek Kuntz from Vishay Siliconics. Hi, Derek.
Bob. Good to see you, sir.
Welcome.
Hey, Derek. How you doing?
Paul. Good.
Pleasure to meet you.
Well, you've been talking about resistors.
True.
And I'd like to come in and start talking a little bit about some MOSFETs and what we've done with the Siliconics technology lately.
I got an application for a MOSFET. I'll ask you after the session, okay?
Sounds great. I'll be glad to answer those questions for you. One of the first things I'd like to talk about, the new technology, is our WFET product. And what we've been able to do is actually go from the traditional QG curve from a traditional FET and actually cut down the QGD by 1/2.
Now what's Q? Q is this?
Charge?
QG is the gate charge.
Instead of CISS.
Right. If you look at the CISS on a data sheet, it varies depending upon the VDS. But when you look at the QG, it's fixed.
Takes that variance
Right.
out.
It's pretty much a stable value.
So how many electrons you have to throw on that gate to get this
Get the
baby to
device
switch?
turned on.
All right.
And so typically when we look at a QGS curve, you have QGS up to here. This is, and then the QGD is the plateau. So on the traditional FET, when you look at the VDS, we'll actually start dropping about where the QGS ends and continue on out.
And you're done switching at the
And
end of
then
that
you're
plateau.
switching. So this is your whole switching cycle.
That's
But
the blue
with-
plateau.
With the blue. When we go with the WFET product, we actually, since we've cut this down, the switching time now gets cut down much faster. Wow. And you get the device to turn on quicker.
Is it that dramatic?
It is that dramatic. We've actually been able to cut down the QGD, like I said, by half, which means some people look at the RDS QG figure of merit, and we've cut that by 60%, and that's at 4.5 volts. This is very good for high frequency switching supplies, pushing up to megahertz and above. We get 1/3 the CRSS on this process, and overall we get a 0.5 to 3% better efficiency when you look at competitive best devices that are out there.
Wow. Now I would see in the CISS, I could compare your FET against a competitor's FET and see the improvement there and that number also?
It's actually the CRSS. Right.
Okay.
The CISS there is an improvement in, but like I said, it's mostly the CRSS that we're affecting on the trench MOSFET.
And that's what you want to look at for
That's
this.
what we want to look at in this sense. The application typically is in a synchronous buck topology, so where we have the input voltage, the output, high side, low side MOSFETs. When we typically run this device, people talk about switching on the high side slowly in order to, one of the issues is to prevent the low side from turning on. So if you have a QGD, QGS ratio of about 1, a DVDT at this node tends to turn on the low side
Shoots
device.
through that high side capacitor
Shoots through
there.
the, right, using
And then pulls
shoots
up the
through
gate.
and brings up the gate.
Bad news.
But bringing this QGD down changes this ratio such that you're less than 1, if not actually down to 0.8. It keeps this spike from going up, keeping the MOSFET off, so that you can now switch the high side faster and not have that shoot-through problem that can occur.
And get more efficiency on that high
And
side.
that's where we're getting the more efficiency on that high side.
Lower temperatures, everything starts working.
That's right.
That's great.
Everything gets better. We also have a high cell density process that we've started to introduce. And what this does is it gives us 43% lower RDS than our previous technology.
Wow.
Competitors did jump ahead for a short time, and it actually gives us about 17% less than competitors in terms of the sheet resistance for MOSFETs.
That's great.
So again, when you look at this figure of merit, we're down about 25% less of what we used to do at the 4.5 volts. Some people look at a figure of merit of milliohms per square millimeters. We're down to 12 milliohms per square millimeters.
That's on the metallization on top of the die?
That's the actual MOSFET itself, so the high cell density. So when you look at an SO8 package, 30 volt VDS, 20 volt VGS, we've gotten at 10 volts VGS, we've gotten the typical RDS down to about 2.4 milliohms, maximum's 3 milliohms. So, SO8 MOSFET, we're getting down to D square pack RDS values. And when you look at 4.5 volts, because a lot of people use the SO8s in notebook applications, we're down to about 3.2 milliohms for a low side device. So we get very good performance in this category.
And these are 20 volt parts, 12 volt parts?
30 volt VDS.
30 volts?
30 volt
With those
VDS.
kind of on resistance?
With those on resistances.
Good Lord, that's great.
And again, this QGD-QGS ratio is very important, so we're keeping that ratio down at 0.8 or less, so we prevent that shoot-through problem. And since we're using this in power supplies, power is an issue. So the next thing we have is a packaging technology, and we have our power pack devices, singles and duals, and we even go down to a 1212 package size. So here we've actually, with the SO8 packages, whoops, let me straighten that out. With the SO8 packages, right?
These guys,
here,
these two right
those
here.
two guys.
And this one's split because those are two devices?
That's actually a dual. We're the only ones with the power pack device or
and
a thermal
it's
device.
electrically dual, in other words.
Isolated,
they're completely separate.
Two isolated devices.
In one package.
That's right.
They're two thermal paths if you wanted that.
That's right. We even have some devices where we connect the source
That's
drain
this guy right
internally, so indirectly you get that connection inside the FET. So we've got a lot of variations even in the SO8 duals.
That's great.
So, but the power pack gives us the thermal performance, the theta JC of a D-pack product. 50, compared to D-pack that's on here, which is a lower device, I believe. You could see that you're at less than 50% the footprint, less than 50% thinner. With the power pack, you're 37% thinner compared to a traditional SO8. This is, again, singles and duals. We're JEDEC registered now. So putting all that together, theta JA from 50 to 37 degrees C for junction to ambient, which is a very good improvement. We have a huge selection of RDS values from, again, 2.4 milliohms, running all the way up to 20, 15, 20, 30 milliohms, whatever you need. And for that dual device that you mentioned, we actually can get down to 13 milliohms at 4.5 volts.
Boy, the circuit board traces start to be a problem.
Yeah,
man.
it gets a little tricky at that point.
You've done such a great job.
Traces? You got to use island.
Island. Now, normally, the source is the big pad. Is the
the drain is the big pad in this case. We are doing some other devices that'll be a little bit different, but we'll talk about that at another time when things get released in that category.
Okay, great.
So, but we have a huge selection of our products, and so putting all this together, the WFET, the high cell density, and the power pack device, you can actually get a 2.2 milliohm MOSFET, which is better performance than you can get in a D-pack at this point. So, I mean, it's very impressive where we're going, and we're just stepping ahead even faster each time.
We're making the power guys' job easy with these kind of parts.
It becomes very easy for these guys, yes.
Very good.
All right.
Well, thank you for that start. Now, we have another opportunity before we go to the lab, to have Paul Rako comment on our other sponsors.
This segment is brought to you, the lab segment that we're going to do right now, which is pretty fascinating. It's brought to you by Reed Electronics, who publishes EDN and other fine trade papers, and Aero Distributing Company, Aero Electronics. They are a distributor for both National and for Vishay.
Thank you. Now we're going to talk a little bit about the theory of this motor before we actually go look at the motor. The theory says that if you have an ordinary AC motor, it has a run winding and has a start winding, and when you want to start it, when you apply power first, the centrifugal switch is doing nothing. This is shorted out. The start winding carries a lot of current, and it gets a lot of torque to bring the motor up to speed. As soon as it comes up near speed, the switch opens up. The start winding has no work to do, and it runs forever. And my theory is if you have this kind of a motor, you can add on 20 microfarads across the centrifugal switch, which will provide extra torque, extra power, and it will run cooler, it will run more efficiently, it will draw less current and less watts. That's a good theory. I like that theory, with a minor problem that the motor I have doesn't do that, even though the theory says you can improve the overall efficiency. The motor I have with me today, I can't add a capacitor because it already has a capacitor in a capacitor start system. You can throw that one away. Let's go over and look at that motor. Come on over. And we'll look at this motor. Now, the first thing we're going to show you is there really is a motor in here, and it really is a fan. And it goes around and around. Oh, boy. What do we have to plug in?
Oh, we could plug it in or anywhere.
Let's plug it in the wattmeter. I got it. So this is a centrifugal two-stage blower motor for a reed organ, for making reed organ music, if you like that sort of thing. Let's drop the screw in here. I connected out the yellow, red, and blue wires from the capacitor. So you drop in a couple of those screws, Paul. I think that's close enough. Just so the cover doesn't hop up and down. This is all labeled,
Hey, Paul,
danger fingers,
you
keep
want to automate
away.
this?
No.
Chuck that baby in here, man. You'll be
And it's
fired in a
connected
minute.
over here.
All right.
The capacitor internally is connected to those two wires, and the wire to the start winding is a link here. If you pull this thing out, it don't start. If you put it in, it will start. Got a couple of those. That's pretty good.
This is where I wanted to set the firecracker off.
Yeah,
I
that's
forgot
okay.
to bring it in today.
Now, here is the Wattmeter. Oh, maybe you can drop the camera on this one. I was mentioning this sort of a squirrel cage or bird cage winding of milliohms. It looks a little bit beat up because I kept trying to get different calibration on it. But this is the 1 milliohm winding. This is the 10 milliohm winding is here, 100 milliohms here, and 1 ohm or 0.9 ohms is here. And these are the different ranges of the switch.
What's this plastic? What is this
This is
thing?
a box that they process and carry wafers around in.
Oh, that's what the slots are.
This is not an LED, that is a neon lamp to remind you that there's a lot of volts there. This guy has a couple hundred volts. This we measured is about a volt. So it's not a big deal. So when we plug this in, we will have, it'll probably read about 600 watts, less than a horsepower. Ready, set. 600 watts, 480 watts, 2 amperes, 480 watts. Now, when I choke it up, it draws less power. So, centrifugal fan draws less power when you load it or choke it. Choked off, now we open it up. And that's all we need from the fan for today. But eventually I hope to show that a similar motor that has an ordinary start winding can have less power by using a capacitor. And we have all these capacitors, 32 microfarads and 1,000 microfarads and whatever it is, 15 microfarads. I'm going to fool around to get the motor to draw less power even though the speed does not change.
Those are AC rated capacitors, I bet.
Those are high voltage AC rated capacitors.
If you try this at home, you'll blow them up if you use DC.
You don't use ordinary capacitors, no. Now, this meter will read certain things. What's a good thing here? Oh, soldering iron. Let's bring the soldering iron over here and plug it in. 26.5 watts. 25.1 watts. Now, will it read? No, it doesn't read. It does not read right on this range. It's nonlinear. But when it reads 25 watts, oh, this is a 15 watt scale. 150 watt scale. So it should not even be
But it
beyond
still
this
works
range.
pretty good.
It's still working pretty
The
good.
one that read wrong was because it was getting into the curved part of that linearity.
Yes.
That's what was going on there.
Okay, I'll go plug this soldering iron. Always keep a soldering iron just in case we need it. And we also keep a hammer in case something really needs, we need a persuader to make sure it's going to work. We just talk to it and it will. It had better work, or else.
We don't force it, we use a bigger hammer.
I haven't got a bigger hammer.
Plugged in.
Oh, I want to plug it in over here.
Okay.
I'm not going to drill a hole in anything. I'm just going to show that. 60 watts. 60 watts. Ouch! 65 watts. Extra 5 watts warms up my hand real fast. What else we got to plug in? Oh, we got 2 things more to plug in. We got a, let's see, does this work right? Yeah, it should work. Look at that.
No power.
0.2 watts.
It's magic.
Isn't that amazing?
What's going on, Bob?
What's going on? I hit a diode in there, a 1N4004. So if you plug it in the wrong way, and you plug it in the right way, and you take the average, it's about 15 watts.
That reads 30.8.
Well, it's because it's the average of nothing and 30.
Because you're only doing the half cycle.
We're doing half cycle. If we take the drill and plug it in forwards and backwards, it'll read about the same. So this does not read about the same because I cheated and hit a diode in there.
So it is RMS, so the half cycle doesn't have to be a sine wave.
It's true.
It could be arbitrary and it'll
And
still
not only
measure
that,
correctly. What a cool thing.
We have a capacitor. Now, capacitor is supposed to not get hot.
Stand back.
No, this is a real 400 volt capacitor. Is it 400? 250. So we got plenty of voltage.
Put it near me.
Nah. No, plug it in. And it reads 0.03, 0.02, almost no change. Now, I can plug this in this way. Plug it in this way. Nothing. Now this is 15.01 watts. So that's probably 0.06 watts. And it doesn't really care. Now the first time I plugged in one of these capacitors and put it on the lowest range, I blew it all up because you put 200 volts instantaneous across a 22 ohm resistor, and it really is a little tough. But now we have it clamped so it won't blow up.
We're wearing safety contacts, by the way. You should always wear safety glasses the first
contacts.
time you plug it in.
So we fooled around with this and this and this and this, and I think we covered everything.
This is great.
So it's not a bad wattmeter. It is not a precision wattmeter yet. Maybe we can get some of those Vishay resistors in there. We will have it a precision wattmeter. Take
We'll
a little
work on
while.
that. We could do a follow-up on the web.
And we will also probably get a audio bandwidth circuit working. Okay, let's wander back.
Can we tilt it for the camera to look inside? I think that's really cool right there.
Yeah, wait a minute. Let's unplug that one. I think so. This is a red wire, but this red wire is hot, and this red wire is not. It's just one little integrated circuit down there, LM394. A few resistors, switches, gang switches, calibration pots. And these are the shunt resistors, which are not very fancy, but they'll work.
I was worried about getting electrocuted on the squirrel cage there, and Bob showed me how to take a voltmeter from the ground prong here on the
There's no voltage
on the thing to measure there, because this is on the neutral side. The Variac doesn't isolate, so you got to be careful around this stuff.
Variacs normally do not
But
isolate.
we made sure we plugged it in the right way so that this is on the neutral leg and hence at a volt or two.
Yeah. Okay, let's wander back here.
All right, come on, Paul.
What else? We're almost done for the day. We are almost done. We went through the electric drill, the light bulb, and the capacitor. And this bucket is called Endgame. Ah, yes, reminder. Ask questions. There's supposed to be a link on your computer screen where you can hit that, and it will lead you to a place where you can type out any questions, which we will try to answer by email. Don't forget to sign up for linear seminars at the web address indicated. Thank you very much. Thank you from Bob Pease and all the application staff at National Semiconductor, including Paul Grohe and Paul Rako. And thank you. Bye-bye.